Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. So, today we will learn chapter 4 part 1. It is about instruction cycles. Okay. We already covered in chapter 3 about machine cycles and instruction cycles. There is a slight difference between instruction cycles and machine cycles. Machine cycles just include the clock cycle for read memory, okay, write memory, IO read and also IO write. But instruction cycles is the complete process from fetch instruction until execute the instruction. Okay, so this is what I talk about instruction cycles. Actually, from fetch until we execute the instructions. It is a complete task for the CPU. Okay, so I want you to refer to the RP notes, chapter 6, part 1. Because here I just do the summarize. Okay, and then you can read LMC concept, but I prefer understanding it technically based on the real hardware. Okay, however, don't worry, it is not difficult because you already learned in chapter 3, memory operations. Okay, as I told you, I prefer to show you in a real hardware, means I will show you in 8086. Okay, because we learn 8086, so it is good for you to understand how it works. Okay, so this program, we write this program using assembly language. Okay, and then when you compile, so the assembler will convert this assembly language to the machine code. Why? Because micro-P only understand machine language, okay, or binary code. This is actually a binary code, but for us, it is quite hard to represent in binary. So it is easier for us to see in hexa value. Okay, so in list file, you can see the machine code. So this is the memory address and this is the code. So every row, it will correspond to the assembly language. So for the machine code B8AB32, actually it is a move AX32ABH. Okay, and then we have 051111, it is add AX1111H, and then C3 is return. Okay, before we go to the simulator, so we can sketch, we can illustrate our machine code to the memory like this. Because our origin start with 100, so it must be started in 100. However, our memory, okay, it is a 20-bit address. So you have to convert to the 20-bit physical address, where you should have shift CS and then you plus with IP and then you get the 20-bit physical address 7100, as you can see in the simulator. Okay, so B8AB32 is represent the assembly language move AX32AB, and then 051111 is add AX1111. Okay, this is in our memory. Okay, this is the address and this is the code. Okay, this is the instruction. But instruction what we write, and it changed to the machine code so that the micro-P can understand. Okay, so from this machine code, we can identify which opcode, which operand. Okay, so if you look at the value here, okay, it is come from 3 to AB, and this value come from this. Okay, that's mean these values represents operand. Okay, and opcode, operation code, normally refer to the instruction. So BX actually refer to the move, and then 05 refer to the add. Okay, so if you change the value, okay, this you change. Let's say you put move AB 1000. So let's say example, but the move opcode will remain same, BX. Okay, this is how you differentiate between opcode and operand. Okay, this is opcode, this is operand. Okay, based on your assembly language. Okay, so move, we already look at the instruction set, move. And then we don't cover yet add instruction. As long as you understand the instruction set, so you can write properly. You can understand. Okay, add is actually you do the addition. And then operand 1 will be equal to operand 1 plus operand 2. So let's say you use add register, comma register, or you choose add AX BX. So what happened? AX will be equal to AX plus BX. Okay. Okay, now we want to look at the instruction cycles. So we have two instructions. Okay, first it will execute instruction move AX, and then it will execute add AX. Okay, first we should know the architecture of OX6. Okay, this is microcomputer system as I shown you before. Okay, this is our micro-P. Okay, this is a pin out of a microprocessor, and then we have memory address register, address decoder, and then we have address of memory here and the data inside the memory. And this one is memory data register or memory buffer register. Okay, this diagram will help you to understand how it works, how the fetch, execute, cycles operate. Okay, as we know, the instructions are in the memory starting at the address 7100. Okay, this is our machine code. Okay, with its address. Okay, first we micro-P should fetch the first instruction. So what it does, first PC or IP in AOX6, it will point to the first instruction. So where is our first instruction? Our first instruction at 7100. So before we execute, the PC already show to the address to be fetched before execute. This is the first step. Okay, and then this address will be inserted into MAR. So the value same, and then it will goes to the address 7100, and then it will take the data inside it. So we have a data B8, and we will put into memory data register B8. And then what happened? We have to bring it to the IR B8. Okay. So before that, this is from CU, also IR CU also. Okay. Because micro-P should know it needs to access to the memory. So the signal, this signal must be activated. So memory must be equal to 1, read must be equal to 0. It means it is a memory read operation. Okay, now what what the micro P is doing, actually it is read the memory. Okay, and then it compared to the microcode in CU. However, it is incomplete code. Okay, so what happened? Mar will take this value next, 7101. Okay, 7101, and M must be equal to 1 and read equal to 0 because it is a memory read operation. And then MDR will take AB value and then it will put into IR. So IR will have B8 and AB. Okay. And it compared to the microcode in CU, it is still incomplete code. And then next, same, it will point to the next instruction, 7102. Okay, 7102, and MAR will have 7102, and then it will take the data 32, and then it will put in MDR, and then MDR will bring it to the IR. So the value will be B8, AB32, and it compares to microcode in CU, and it realized that the code is complete. So the code actually it want to execute move AX32AB. Okay, it is a 3-byte instruction. Okay, and then it decode. When the micro P has a complete code as compared to microcode in CU, micro P interprets the code and understand what to do because it's already in microcode in CU. What is microcode? Microcode is a machine code. All the machine code that correspond to the assembly language. So let's say we have move AX, BX, move AX, CX, move AX, DX. So it will have its own microcode. So micro P already know what it should be do. It should be done. Okay, and then next, it has to execute move AX32AB. So what happened? This is just the operation load data into CPU register. So no need to activate the signal here. So what it has to do? So the register AX will have through. Oh sorry, it is supposed to be 32AB. Sorry, typing error. Okay, that is for the first instruction. But look at here, your PC already point to the next instruction. Okay, and then next, it has to fetch next instruction. Next instruction at 7103. And then MAR will have 7103. And then it will goes to the 7103. And then it has 05. 05 will be put into MDR. And this 05 will be right into IR. 05. Okay. And before that, before I forgot, so memory read operation, the signal for memory read operation must be activated. So this is the step. Okay, first PC, and then go to the MAR, and then the signal, and then go to the MDR, and then go to the IR. And then it will compare to the microcode, and it is incomplete code. So MAR will be +1. 7104, it has 11, put 11 in MDR and then put into IR. So we will have 0511. And then it will compare to microcode in CU, it is still incomplete code, and then MAR will increase, 7105, 11. Put again 11 in MDR and then go to the IR. And then your IR will have 051111, and then it compared to the microcode in CU and code is completed. Okay, so it decode when the micro P has a complete code as compared to microcode in CU. Micro P interprets the code and understand what to do. So what it should be to do? It should have to add AX plus 111 and save in AX. Okay. So just now we have 32AB. We plus with 1111, and then we can get 43BC. And the signal no need to activate because it is the operation is just happens in the micro P. Okay, however, okay, but what I showed you just now is the real, based on the real hardware and the assembly language, OXC assembly language. But now, this is for general. So let's say your PC is 12. Okay, this is the process of fetch instruction. Okay, so PC need to put into MAR. Okay, fetch instruction, this is for first instruction. So your MAR will have 12. Okay, this is a memory address. So what we have in 12? So we have 530. So this is the machine code. But the assembly language is load 30. But this is not the real assembly language. So what is, so you can see here 30 represent operand here. But 5 is an opcode. Okay, so what it has to write in IR, it's to write 530. Okay. Okay, now we have a next example. We have PC will be input into MAR. This 45. Okay, and then what the data we have in 45. So we have 599. Okay, 99 is operand. Okay, 5 is opcode. Okay. And then, okay, because this is not the real, so we can assume that 99 is address. So the address is 99. It looks like you want to load from the address 99. Okay, go to the 99. And then what we have 210. 210. And then program counter must point to the next instruction, 46. Okay, for this instruction, okay, load 99. As we know, its machine code is 599. 599 here is load 99. So for this course, make sure this instruction you assume looks like move AL 99 H or AH or AX. Okay. So you can assume that this instruction represent move AL 99H. So when you see here, this is the memory. Okay, that's why we put MAR just now. MAR is 99 because we have to go to the address 99, and then at the address 99 we have the data that is 210. So the value 210 we want to put into A. Okay.